Greetings from the Space Telescope Science Institute to all of our astronomy enthusiasts joining us for today's webinar. We're here today to tell you the story behind the headlines of this week's photo release of Hubble Space Telescope's deepest view of the universe. Three members of the team of scientists who put together this image are here with us today. Each of them will give brief presentations, followed by questions from our viewers. You can send questions via YouTube or the Google Events page. Let me introduce our panelists. We have Dr. Garth Illingworth, Mr. Dan McGee, and Dr. Pascal Oesch. They are all at the University of California, Santa Cruz. And let me hand it off to Dr. Illingworth.
Thank you very much, Ray. And so I would like to walk through a presentation that we've put together. The three of us will do that in sequence, and to give you a little background about this remarkable new extreme deep field. And so if I could have the next slide, please. So Hubble's extraordinary XDF, and it certainly is extraordinary. This is the deepest ever image taken of the sky. It involves an exposure of 2 million seconds. If you think about your iPhone or your camera, you typically take exposures that are 1/100th of a second. So this is quite a contrast. What it involves is 10 years of images from Hubble's cameras. And Hubble's cameras are really twofold. In 2002, the astronauts took up the new advanced camera at that time. And then in 2009, a new wide field camera 3. And these two cameras complement each other. And can I have the next slide? And we'll explain a little about this. So making the XDF. The XDF started with the Hubble Ultra Deep Field, which was taken largely in 2003 using the new advanced camera. It takes optical images and went incredibly deep. Then in 2009 and 10, when the new wide field camera 3 became available, the Hubble Ultra Deep Field 09 was taken. This extended the wave bands, extended to the red the information available, and opened up a whole new area. In addition to these images, there are numerous other images that have been taken over the decade with these cameras on the Hubble Ultra Deep Field area. And so what we did was took all this data, all this remarkable number of images, combined it to make the XDF. And Dr. Dan McGee will a little later explain how this was all put together. Could I have the next slide, please? So why are we interested in the XDF? These ultra-deep images, which the XDF is the prime example, is the ultimate example, as it were, at this time, is key to understanding the origins of galaxies. If you look in the upper right, there's an image of Andromeda, our nearest neighbor, a huge spiral galaxy, much like our own. So how did these galaxies, like the Andromeda, like the Milky Way, come about? So that's the question that we astronomers, many groups are doing, is searching for the first galaxies, the earliest galaxies, and trying to understand when and how galaxies formed and how they grow over time. Ultimately, we're trying to understand the origins of galaxies. Next slide, please. So how do early galaxies compare to those of today? So in the upper right, again, Andromeda, and then there's a representative early galaxy. This is not exactly like an early galaxy. We can't see that level of detail, but this is one that is probably very much like those that we're looking at the very limits of the ultra deep field and of the XDF. So early galaxies are full of bright young blue stars. They're forming lots of new stars. They're growing very rapidly, but they are very small. They're very different. They're about 1/10 the size, 1% of the mass, and with none of the beautiful regularity that we see in galaxies like Andromeda or our Milky Way. Next slide, please. So how is it that we can learn about galaxies from these telescopes like Hubble? Hubble is really a time machine. These galaxies, these early galaxies, are so distant that light takes so long to reach us that we are actually seeing the galaxies at a very much earlier time in their development. And in fact, it's like looking back to when we were younger as people. So XDF allows us to look back in time through 96% of the life of the universe, a remarkable achievement for humankind to think that we could actually do that with the Hubble telescope. So we actually see galaxies that are forming 13.2 billion years ago. This is remarkable. This is just 450 million years after the Big Bang, which itself was about 13.7 billion years ago. In the upper right is a picture, an image of the most distant galaxy we know today. This is a great search going on for other examples like this, and we'll talk more about these later on in the presentation. Next slide, please. So what we're trying to do here is really a path of exploration. We're reaching out to explore for galaxies when the universe was young. XDF allows us to do that and to take steps beyond what we could do with the original Hubble Ultra Deep Field. That could only take us back to within about 1 billion years after the Big Bang. But the first galaxies, the earliest galaxies, and some of the most dramatic changes in the universe occurred even earlier than that time. And so with XDF, this allows us to explore to even earlier times in the Hubble Ultra Deep Field. And Dr. Ersch will explain a little about this in his presentation. Next slide, please. But before we get into the science, I'd like to hand over to Dan McGee to tell you how this remarkable image was put together. Dan?
Thanks, Garth. So I just want to give you a little background about how we put all of this data together. And to start with, this slide here shows where the extreme deep field is located, and it's in a southern constellation of Fornax in the southern part of the sky. Next slide, please. And the XDF is actually just a teeny portion of the sky, and to show an example of this, in this slide we show the full moon and then the area covered by the XDF, and you can see in this slide that the XDF is actually only about less than 1/10 of the area that is covered by the full moon. Next slide, please. So Hubble has spent more time observing the XDF than any other place in the sky. And the observations that were used to create the XDF were taken about over a 10-year period, from July of 2002 to about March of this year. And over that 10-year period, Hubble observed the XDF for about 50 days. And during those 50 days of pointing at the XDF, the Hubble took over 2,000 exposures in 8 different filters on 2 different cameras, the advanced camera for surveys using the wide field channel, and the wide field camera 3 infrared channel. And so adding all these exposure up, we get about 2 million seconds of exposure time. Next slide. So to create the XDF, we had to gather a lot of data. We took all the data covering the Hubble Ultra Deep Field and in the surrounding area around it, and it took actually quite a bit of time to download all this data from the Hubble archive. We had to ask for it in small little bits, so we didn't, so we could get them in a reasonable time and not totally mess up the archive by asking for all of it at once. So after downloading all that data, we ended up with about 250 gigabytes of images that we needed to process. Next slide, please. So here, in this slide here, I want to show you, so this is an outline of the original Hubble Deep Field that was taken in 2003 and some in 2004. So these blue outlines here show you the advanced cameras for survey observations that were taken during that time. Next slide. And now adding on to that area, so in the outlined in red here, we show you the data that was taken with the wide field camera 3 infrared channel in 2009 and 2010, as Garth said. Next slide. And so, as Garth said before, a lot of other data has been taken over this field over the last decade, and so this slide sort of shows you the outlines of all of the other sort of exposures that have been taken, and that we include in the XDF. And next slide. And so in generating the XDF, we added all this data together and combined it. And so the area in orange just shows you the area that's covered by the XDF. Next slide. So before we started processing all this data, we had to do some things. We actually had to visually inspect all of the 2,000 exposures that were taken. So the reason we had to do that is we were looking for problems in exposures, and occasionally you get artifacts in image. And as an example of that, you know, when you're taking an exposure with Hubble, occasionally a satellite that's orbiting above Hubble's orbit will actually pass through the field of view while you're observing and taking exposure. And what happens is you'll get a streak across the image. And so that's sort of the things we look out for, and we have to mask those things out so we don't include those artifacts in the final combined images. And the next step in the processing is we actually have to align all these images together. You know, Hubble is pretty good has pretty good accuracy when pointing at a certain part of the sky, but to actually combine all these images together and to make them scientifically useful, you have to do it with a much higher accuracy than just the Hubble pointings. So we had software and computer programs that we have written that we actually go through each of the exposures and identify objects in those exposures, and then we compare every other exposure with each exposure, and we determine actually how much we need to either shift an exposure or we may have to actually shift and rotate it slightly so they align up perfectly. Next slide, please. So after we've got that figured out how, once we've got them all aligned, we need to combine these images. And to do that, we use a computer program that was written by the Space Telescope called Drizzle. And all Drizzle does is, well, we could feed it different exposures from different filters. And we've gone through the step to make sure that they were all matched up with each other, and then we can stack them and actually create a nice mosaic image from each filter. And then, you know, and this is done in an optimal way in a process that's called drizzling. And then from there, we have a final mosaic picture from each exposure, and we can use those mosaic pictures to actually create a final color picture using the different filters, images of the different filters. So at that point, that's where the image processing ends, and we can actually start doing science on these images. And I'd like to now turn it over to Pascal.
Okay, thanks, Dan. Yeah, so Garth already gave you a nice overview of the type of science that we can do with this new image. And I just want to go a little more into the details, and in particular of how we can actually find these first generations of galaxies with this image. But of course, this is only a small part of what astronomers are doing and what astronomers are using this image for, and we cannot cover all this today. And so as Garth and Dan were pointing out, the new XDF image essentially builds on the old Hubble Ultra Deep Field image that was taken with the ACS camera. And the ACS camera is sensitive to light in the optical wavelength range, where we can see also with our eyes. And now with the XDF, we are extending this to longer wavelengths and to the near infrared, because the new we cannot see there with our eyes, but the new camera, the V3 camera, is really efficient at studying that light and detecting it. And so this is really important if you want to study galaxies in the very early universe, more than 800 million years, earlier than 800 million years after the Big Bang. And because these galaxies that you can see there as the shaded gray area, these galaxies are completely invisible in the Hubble Ultra Deep Field. And we really need these near-infrared images to detect them. And so on the next slide, I just have a little example of this. On the left, there's the previous image, the Hubble Ultra Deep Field, the optical image. And you can see in this circle, there's just nothing there. While in the new image, in the XDF on the right, you can see this bright red dot, which is one of the most distant galaxies that we have detected in this image. And if you have seen the fly-through video that was released together with this image, this is the one galaxy that the image essentially that the video essentially ends on. And so on the next slide, essentially I just marked up the positions of all these very early sources, more than 800 million years from the Big Bang. And so you can see by studying, there's a lot of these sources here. There are 60 sources essentially that we identified in this image alone. And so these are very important because these are the galaxies that really changed the early universe. They ionized all the hydrogen gas that is around, that is filling up the universe. And by studying the properties of these sources, how big they are, how they look like, and so on, we can get a lot of information about how today's galaxies, like our own Milky Way, have been building up over time, starting from these very, very early times. And so on the next slide, essentially, I show you, essentially, if you want to go out and look for these sources yourself in this new image, you can do that. And you just have to go and look for red galaxies, red dots in this image. One problem there is that red galaxy colors can also be a sign for old stars or for a lot of dust. And so you have to be a little bit careful there. And so on the left, there are two examples of sources that are only about 6 billion years away from us, while only the very source on the very right is 13 billion light years away. Okay, and so on the next slide, we see again the wavelength coverage of the XDF field, of the XDF image, and as you can see, now Hubble is really reaching its limit for finding even earlier galaxies than what we can see with the XDF. And the problem here is, you can see in the shaded gray area again, the further we go back in time, the farther to the red the galaxy light is shifted. And this is just a consequence of the expansion of our universe. And so galaxies about more than, or earlier than 400 million years from the Big Bang, essentially, they will remain invisible to Hubble's cameras because they will shift out of the view of the XDF. And so we really need a JWST, and JWST will do a great job to push even further to discover the first galaxies, because it's just 100 times more efficient than the Hubble Space Telescope itself. And so this is going to be a very, very exciting time, and we're all looking forward to that. Thanks.
Okay, I want to thank our three experts for telling you how they put this wonderful observation together. It's hard to imagine that 20 years ago, before Hubble went up, we could only see, I think, roughly halfway across the universe, and to be sitting here today talking about galaxies at such tremendous distances is amazing. Now it's your turn to ask these experts any questions you want, and again, let me remind our viewers, you can send us questions via YouTube or the Google Events page. And with that, let me go to the first question from one of our audience. You're calling this the extreme deep field, but can Hubble go deeper still? Are any astronomers or teams of astronomers now using Hubble, looking at Hubble, using Hubble to look at the deep field now and trying to push back that limit?
Certainly, Ray. This has been an ongoing process, as we've noted, that this is 10 years of observations of Hubble on this area have been built up into the extreme deep field. And so what we're, of course, hoping for over the next many years of Hubble's life, that yet more data comes in and we add it to the field to make it even deeper still. In fact, there is some data coming in from the infrared camera in particular this fall that will become available to the public and to all astronomers late this year and early next. And that can be added in, and that will add new information. So we continue to hope that more will be added, that we'll be able to push a little fainter and deeper. What we probably can't do is we can't push out much closer to the Big Bang. That's really a limiting aspect of the current cameras on Hubble. And to go closer to the Big Bang to earlier times, we really need the James Webb Space Telescope. But the new data will give us the opportunity to explore the universe in the first billion years in more detail, which will be great.
Okay, the next question I have is, how much farther in terms of years? What will the Webb show you that you can't see in these Hubble pictures?
That's a fascinating question. Fascinating. You know, ultimately, we would really like to see the first stars and galaxies with Hubble, with James Webb. Very challenging. We certainly expect that we'll be able to push back a few 100 million years earlier and see galaxies in formation, but exactly what the universe holds for us in those early times is something that JWST will reveal, and at the moment it's merely a matter of speculation and imagination. So
That's
we're
great.
looking forward to fascinating things. Pascal, did you have anything you wanted to add on that?
No, essentially, as Garth was saying, what we see now with the XDF and with the Hubble images, we see that galaxies, there are still galaxies, even as we push out to these early times, and so there will, and they have stars in them that have formed earlier than that, and so there will be more galaxies out there that we can detect with JWST further back in time. So, yeah.
Okay, great. Here's an interesting question. If you were to aim Hubble in the opposite direction, would the universe look the same? Would you see a different age? Do you expect anything would look different?
We'd see different galaxies, of course, but the universe is basically the same in any direction. And numerous experiments and tests and observations have shown that to be the case. But of course, not in detail. We would see different galaxies, different objects, and we would love to explore some other very deep field because we need other areas to build up the numbers of galaxies in the samples. So more deep fields like the XDF would be incredibly good to have, but a challenge. It takes a lot of time, as you've seen. 2,000 exposures on Hubble, 2 million seconds, that's a lot of time.
Could any of you talk a bit about how much time it would take with the James Webb to do the same kind of observation?
We've typically used about a factor of 100 gain with James Webb for typical imaging capabilities. So it's a lot less, so thousands of seconds. So in fact, hours would achieve what we've done already, which is really quite remarkable. James Webb is astonishingly powerful, will be astonishingly powerful when it launches in 2018.
So the next question from one of our viewers has, the field is full of galaxies, and you showed us it's a little tiny piece of the sky. Has it changed your estimate for the number of galaxies in the entire universe?
Pascal, did you want to answer that? And I could add to it afterwards.
So essentially, as I was showing, now with this new image, with the new camera, we are able to push to earlier times, and in particular, these earlier times, we found that there might be many more fainter galaxies, the galaxies we cannot currently see with Hubble. But so we are really at the limit of our detection of this image that we have now. It seems like there are more galaxies than what we expected before at these early times, and more fainter galaxies. So and again, these we will be able to detect with James Webb very easily and quickly, and so that's going to be great. Garth, did you want to say something more?
Yeah, let me just add to that. I think one of the things that XDF has really taught us over the last few years is we've taken the data that has become the basis for XDF, is that the universe is just full of tiny little galaxies in early times. And it's these tiny little galaxies where most of the mass is, where most of the light is. So these are very important to study. So these extremely deep fields are crucial to understanding what's happening in the early universe and how galaxies are building up.
Okay, great. We got our next question. In terms of redshift, which is a measure of how far away the galaxies are, at what redshift do you expect there to be a sudden drop-off in the number of galaxies, an epoch where galaxies are just beginning to start forming? Do you have any prediction for that?
This is an interesting question because we've recently started to look at the galaxies around 450 million years ago, where there's now just 2 objects that are really part of that sample, and galaxies at 600, 700 million years ago. And there appear to be fewer of those than we might expect, but clearly the numbers are very small. So there's a time in there around Redshift 10, for the folks who asked about Redshift, where things may be changing. But what we really expect is that the big changes will occur around Redshift 12, 13, 15, at the times when the very first galaxies are starting to build up. So we may be getting a hint from Hubble already of those changes, but it's still a region that needs more explanation, more exploration. And in fact, the new data that is coming in and will become available later this year to everybody should give us some clues about that as well, should it maybe increase the number of those objects around Redshift 10. Pascal, did you want to add to that?
Oh, no, I think that's a very good answer.
Okay, this is a fascinating question. This is very imaginative. Let me remind the viewers that Hubble and Webb will look out to a certain redshift. Beyond that is the background glow from the Big Bang itself, called the microwave background. So one viewer asks, could you have a microwave telescope or some kind of telescope to look even farther than the Big Bang radiation?
Certainly, further than the Big Bang. No, that's an
well, before the Big Bang, but
I think we're bordering into philosophy here.
Okay, well, not
physics lets us explore back close to the Big Bang,
right,
but
yeah.
Earlier times, I think this is for theorists and philosophers.
How many? Can you tell us how many? A feel for how many astronomers and teams of astronomers have been using this data from the past 10 years, and how many papers and discoveries have come out from all that?
Wow, in total, I'm not sure. It's interesting. I know that when the Hubble Ultra Deep Field 09 data came out with Wide Field Camera 3 with the infrared, that was elicited a lot of interest. It was a public data set. I think 6 or 7 groups of people have been working on that and publishing papers, and there's over 40 papers that have come out just in the last, let me see, 2.5 years since that data set became completely available. So these, and of course there are a huge number more now when you add in all the Hubble Ultra Deep Field data from 2003 and 4. So I would estimate hundreds of papers have come out, but I actually don't have at my fingertips the number. Pascal, do you have a better estimate?
No, sorry. I also don't know. There's a lot of people, and of course you can do so much more than what we are just saying here. Then you can study galaxies at slightly later times as well, and you can see those in detail that we haven't been able to see before. So there's a lot that people are doing.
Yeah, that's actually a very good point. These data sets have value from galaxies all very close to us to at the earliest reaches of the universe. And so they've been studied by a very large number of people and used very extensively throughout the community of astronomers and physicists, astrophysicists who are studying galaxies.
Okay, great. Here's a very good question. We've put out pictures from Hubble where space is warped and the light of galaxies is warped by a phenomenon called gravitational lensing. Do you see any evidence of gravitational lensing in the XDF?
No, not as far as I can recall or as far as we've seen. We're looking at a very tiny region of space, and particularly this field was chosen originally to minimize having particular condensations of galaxies called clusters of galaxies, which is where we would most obviously see the gravitational lensing. There will be some effect from lensing, but it's a relatively small effect, very minor on this scale. It's something that you would have to search extremely hard for. It's what people might call weak lensing, and its effects on the galaxies are really, really tiny. Pascal, do you want to add to that?
No, essentially, in order to see gravitational lensing, you need a very, very massive structure in front of you, either cluster or a very massive galaxy. And so, yeah, as Garth was saying, we don't see evidence at all for strong lensing, because these are very particular locations in the sky where you can see that, and not in the ultra field.
Now, this is a very good question, too. When we talk about any of these deep fields, we always talk about distance in terms of billions of light years, but we're also talking about looking back in time, billions of years. Can any of you provide a simple explanation to our viewers how you can look so far back in time? And are you really sure you're looking back in time?
Yeah, I mean, I would say that the way you phrased it there explains it, that the distances are billions of light years. That is, light takes, in a year, will travel a certain distance. The billions of light years is a distance that corresponds to billions of years for the light to reach us. And so it's something that we have calibrated by various means, but it's a way of characterizing the scale, and it is intrinsic to the nature of the physics that light doesn't travel at infinite velocity. It does take time to cover a distance, and that distance then turns into a time that light takes. So an example is the sun is 8 light minutes away. We see the sun as it was 8 minutes ago. So we're seeing these galaxies as they were billions of years ago. It's a big difference, but the principle is the same. Pascal, do you have a nice little explanation that would be good to add here?
No, I think that is good. It is a constant of nature, and the light takes time to reach us and to reach the Hubble Space Telescope, and so that's how we look back in time.
Great. Now, a very common question, and it came up here, is we've seen estimates for the age of the universe, and does the XDF agree with those estimates? Does it help us to refine the age of the universe? The published age is 13.7 billion years, but does the XDF support that value?
Yeah, fortunately, the age of the universe has been determined now very well through a variety of techniques, and particularly using very powerful microwave telescopes. And so this is something that this group sitting here, but astronomers have determined independently. And so we are just using our estimates of the ages of the look-back time and so on, and it's based around that age of the universe. We don't have to come up with an independent, and we couldn't. This is not the sort of data that you use to get the age of the universe.
Mm-hmm. Okay.
Pascal, do you want to add to that?
No, I think that's good.
Now, a question along those lines, that probably among the biggest questions in modern astronomy: what is dark matter and what is dark energy? That force that's pushing the universe apart, and whatever that dark matter is floating out there. Does XDF provide any insights into either of those?
It's interesting that supernova searches, which were used to initially demonstrate that dark energy existed, the universe was behaving in a very unexpected way, were part of those searches occurred around this region. And in fact, so the XDF actually has some images that were taken by the supernova search groups looking for and measuring supernovae. And so we've all incorporated that data, but it's very peripheral. XDF isn't explicitly aimed at trying to understand or to measure dark energy, but it certainly includes some of the data that was used for that. And for dark matter, again, that's something that we explore best with clusters of galaxies as a way of measuring that directly, with weak lensing on large scales, something that the XDF, which is a very focused pencil beam, doesn't look at directly or can't be effectively used for directly. So there are other approaches that were being used for both of these questions. So XDF uses what we understand about dark matter and dark energy to understand about how the galaxies build up and grow, but not directly will it contribute to either of those questions.
Okay, great.
Pascal, your chance as well. Anything you want to add there?
No, I think that's a good question, good answer.
So another question, I mean, I think looking at the XDF, it's one of the most colorful pictures we put out. You've got the Roy G. Biv galaxies everywhere. So somebody asked, what are the green galaxies and why are they green?
Very interesting. So most of the galaxies are blue intrinsically. They appear red because the hydrogen in the universe absorbs the very bluest light and so makes them appear red. So as you look at that, you see some blue galaxies. Most of the others, I would say, are blue. There's also red galaxies in there. Then some of those are just because of this artifact of their hydrogen absorbing light, but some of that is also because there are galaxies, as Pascal explained, that contain older stars and look red. And so there's now a sort of middle ground where there are some galaxies where the stars are aging and they can look green. So they're not necessarily old or extremely distant, and they will look green because of the nature of the stars and of the effect of dust in the galaxy. Pascal, do you want to add to that?
Yeah, so some of these, so as I was showing, and as Garth was saying, the hydrogen is absorbing some of this light of these sources, and so that's why if you go back 800 million years close to the Big Bang, essentially these sources are all red because the light is only emitted at near-infrared wavelengths. As it just goes slightly lower, these galaxies, the same kind of galaxies, they just look very green because they're blue intrinsically, but the light, the very blue light is absorbed. That we don't see that, and so that's why they appear green. They're typically about 1 billion years after the Big Bang. One of the greenest, the galaxies that look the most green are roughly 1 billion years from the Big Bang, and they were already in the Hubble, the original Hubble ultra deep field in the ACS data. We could see those sources already, and there they were looking red actually.
Okay, next question. The theory of the Big Bang, of course, is that space is expanding. So these very distant galaxies you're looking at must have been more crowded. And how far apart from each other do you think they were? Was everything kind of compacted back then?
Yeah, that's very interesting. If by any chance there was anything alive in those days to look at galaxies, galaxies would have looked a lot different. None of these beautiful spiral galaxies, as tried to indicate early in my slides, they would be blobby little things, blue, and they would be much closer to each other. And so the universe would look really very different. The sky at night, if you went out with a telescope and looked around, you would just see more of these very blue, small, bright, very intense galaxies much closer to each other. So it changes over time. Pascal, do you have an image of what you think it's like as you go back?
No, essentially, what we can say is that the universe was only a tenth or so of its size that it is today when we see those galaxies, those early galaxies. But as Garth was saying, the galaxies wouldn't have looked the same as our Milky Way today. So it is tricky to say how they would have looked like.
So along those lines, you see the galaxies that existed billions of years ago. How do we know what they're doing today? Can we figure that out?
Wow, interesting. Most of those are going to have ended up in galaxies like our Milky Way, like Andromeda, like other big red galaxies, big red galaxies around us. So these galaxies at those early times are the seeds from which today's galaxies are built. And so one can't trace the history and exactly where they're going to go to, because one of these little galaxies is probably going to grow somewhat of its own accord as gas falls in and stars form, but then it's going to collide with another galaxy, and there's now going to be a merged galaxy that's going to build up and grow. So they have a long history of activity, merging, growing, coming together, changing, gas falling in, forming the disk. So the growth of galaxies is a very dynamic and dramatic process over the first few billion years until the universe started to look like the galaxies of today.
Yeah,
okay,
sorry.
I'm sorry.
I just wanted to add, essentially we're using our observations for galaxies at different times. So that's because of the constant of speed of light, we can look back in time, as we were saying before. And so we're trying with our observations to connect these different galaxies at different epochs. But of course, we cannot be sure. There's not a one-to-one connection. And so we're using computer simulations in the end of galaxies and of the build-up of the universe, essentially, to decipher these things. And there's a very tight, essentially, interplay between us observers, essentially, and the theorists and the astronomer theorists, essentially, to answer this question.
Yeah.
Okay, I'm going to come back to the microwave background. Yeah, fascinating question. I don't think you can talk in terms of distance, but the difference, I guess, in time between the farthest galaxy in the XUDF and the time of this microwave background when it became transparent. You can express that in years, but not distance, of course, can you?
Yeah, the microwave background, sorry. The microwave background was essentially 400,000 years after the Big Bang. So that was very soon after the Big Bang. And so, and our galaxies are essentially 400 million years then after the Big Bang. So there's, you know, it's a negligible distance almost from the Big Bang to our galaxies that we're observing than from the microwave background to our galaxies. Sorry, Garth.
Yeah, so it's sort of a fascinating discussion because between when the 400,000 years that Pascal mentioned and when the first galaxies formed, which we don't, the first stars and galaxies, we don't know when that is, but maybe it was around 150 million years, 200 million years. There's sort of a period in the universe we call the Dark Ages when nothing was really happening. There were no stars, there was no light, there was just gas permeated through the universe. And so it was a very different time. The universe was very, well, I could say boring almost, in the sense that there wasn't the beauty of the galaxies and stars forming. And then finally, after 100 million years, 150 million years, the first stars came together and very dramatic growth started to occur in the stars and then in the galaxies. And so we refer to that period in there as the Dark Ages. So the first stars and galaxies ended the Dark Ages.
Okay, great. Now here's something dealing again with the Big Bang. All the galaxies you see in the XDF, are they accelerating, and is that acceleration at the same rate?
They're growing along with the universe. And so they are moving apart from each other as the universe grows. None of these galaxies, well, there are galaxies in there that are probably close enough together that they will ultimately come together and merge and make one galaxy. But most of those galaxies are going to be moving apart as the universe grows.
Okay, next question. And again, this gets more into basic physics of the universe. If the universe is expanding, can galaxies overtake other galaxies? And their question was, is the speed of light faster or slower, or some physical parameters changed in that early expansion?
I think the best analogy that I like to carry around is to just think of the universe as, you know, maybe I think the one that we often see in our old textbooks is an expanding loaf of bread as you bake it, or a cake or something, that all the raisins in such a loaf, if you had raisin bread, would be moving apart from each other. As the universe expands with time, essentially the galaxies are carried through space by the universe and increasingly separate from each other. The only reason for them to come together was if they were close enough that the gravitational pull of the two galaxies was strong enough to bring them together. That happens, but that's a small fraction of the time. Pascal, do you have another analogy you like to use?
No, I guess the balloon is a good analogy, that you blow up a balloon, and if you put some points on the balloon, they will all go away from each other, and that's how galaxies are moving apart.
Okay, this is a fascinating question, and this gets, I know you guys use the term variance, I think, but why aren't you looking in the opposite direction just to make sure doing an XUDF in the opposite direction, just to make sure there's no funny asymmetry, you know, and maybe the universe is lopsided, you know. We tell everybody.
Yes, very interesting question. We keep trying. I think I mentioned this earlier, that we really only have one XDF, and it would be great to have more than one, and to have several spread around the sky. But as you saw, there was 50 days of Hubble pointing at this one field to build up these data, and that's a lot of time. And so we would love to take Hubble and point it in the opposite direction or in several other directions in the sky for 50 days each. But it's very competitive to get time on Hubble, and so far we haven't been successful. So we're hoping that the Time Assignment Committee of Astronomers will look favorably on future proposals, and that we get some deeper data in another region. So we welcome any support from any listeners.
This is such a unique field. Is there a competition to try to get orbits in time among astronomers?
Very much so. Hubble, every year astronomers send proposals in to ask for time for Hubble, and there's a huge oversubscription, 5 to 10 to 1, 10 to 1 typically, and so it's extremely hard to get time on Hubble. There's so many different fascinating scientific problems to be done with a space telescope. And this is only one of them, unfortunately. Even though I love this area, I have to say, you know, there's so many different areas that only so much time could be dedicated to this particular one. But we really do hope that we manage to get another deep field or two, particularly in preparation for James Webb Space Telescope. That is really going to look at early times, and it's crucially important that we have a number of these deep fields.
That's actually my next question. How many, since Webb is so much more efficient, are astronomers talking about looking in all different directions and doing the deep fields?
It's interesting. They certainly will do more with Hubble, with James Webb. But Hubble has some unique characteristics that James Webb doesn't. It can look further into the blue than James Webb will be able to. And so it would be very nice to set up, and not just nice, important, to set up several fields where the Hubble unique data could be obtained before James Webb flies. And so we would like to set in place the initial phases of those data, and also to provide some initial deep fields, even in the infrared, so that James Webb can hit the ground running, as it were, so that when it launches, it can immediately start looking at interesting objects to understand them in more detail than we ever can with Hubble or with our ground-based telescopes.
Yeah, one point, sorry, there is also that with the James Webb, we will be able to take spectra, actually, of sources. We can not only take images, but we can take spectra of the sources that we are looking at now. And with that, we can really determine, you know, for sure, the distance of these sources. And while now we have quite a bit of uncertainty, actually, on how far these sources are from us exactly. And so having additional data and additional fields where we can identify such sources will be really important to really just start with JWST to go and look and measure exactly the distance for a lot of these sources immediately after launch.
I'm really delighted with the questions we're getting. We've got a lot of inquiring minds out there. This one's particularly good. They've said there are theories that stars were much more massive in the distance past. Can the XDF show us individual stars, or for that matter, could James Webb in those very early times?
Yeah, I think it's hard for XDF to do that. Even the very massive stars are very difficult to see. James Webb will certainly be able to do better, but I'm not sure that even it could isolate anything but groups of these massive stars. Pascal, what do you think?
Yeah, I don't think with James Webb we can see individual first stars, because these first stars are forming out of gas that is very different from today's gas. It has essentially just hydrogen and helium and nothing else. And so that's why people think that this would be very massive. But I think what James Webb will be able to do is only to see supernovae of this sort, of these very massive stars. So because they're so massive, they will explode very quickly, actually, into a supernova, and this is a very energetic event, of course. And so with James Webb, I think we will be able to see those supernovae, but not individual first stars.
Okay, that makes sense. Okay, let me. This is a fascinating question. If you're an astronaut up in space, and let's assume your eyes are as good as Hubble's, would you see all those colors you see in the XDF picture?
Yes, that's right. I mean, I think you need a little wider range of eyes. Maybe if you had just our normal eyes and look out, galaxies do show different colors and do show quite a bit of variation. Dan, did you want to add to this?
Well, just that we're seeing we're looking outside the visual part of the spectrum with the in the near infrared. So I mean, this color image shows us stuff that we actually can't see with our own eyes, but we would still see colors of galaxies.
Yeah, I suppose to add to that, if we could, the astronauts had extremely good eyes, and they looked around and they could see faint galaxies, distant galaxies, they would show different colors, very much so.
Oh, that's interesting.
Would demonstrate a range of colors. The actual colors there are probably not in the image in the XDF, because it does go into the infrared, and not truly representative of what our eyes would see, but the range of colors from very blue to very red would certainly be visible. It would appear to that way to the astronaut.
That's fascinating, almost like stars, I guess, except that they're color temperature rather than redshift.
Right. Yeah.
This is a more of a philosophical question. We're building this James Webb telescope, and we're going to push farther. When would you say you reached your ultimate goal? All the effort and energy to build these monster telescopes. Is there an ultimate finish line for saying you've gone as far as you can go?
Interesting question. So for a scientist, we're always trying to understand more about what happened in the universe. I would say at the broadest level that what James Webb is setting out to do to understand the first galaxies and stars is, for this area, sort of a penultimate goal, that we really would like to see the first galaxies, see stars forming in those. James Webb will go a long way towards that. Will it be able to see the first stars? Probably not. And so, maybe one would like to see a successor to James Webb that's even better, bigger and better. But it does depend a lot on the question. James Webb is obviously going to play a role in searching for planets and trying to understand the nature of planets around nearby stars. Can it really do that extremely well? It will make a lot of advances, but that's an extraordinarily challenging problem, and to do that properly will probably require a telescope way beyond the capabilities of James Webb and beyond what we can probably build even right now. There's a lot of development needed for that. So it does depend on the nature of the question and the part of astronomy. But there's no doubt for distant galaxies, understanding what's going on in the early universe, James Webb is going to be an amazing leap forward. 100 times Hubble, 1,000 times the Spitzer Space Telescope. These are stupendous gains. Pascal, did you want to add anything to that one?
No. James Webb will be great, but it won't be the end, of course, to understand our whole universe. There's a lot more needed.
Yeah, let me add just one other thought which just came up on this too, is that we're embarking on a new generation of major telescopes on the ground, 30, 40-meter telescopes. These will have capabilities for spectroscopy, for looking in detail at individual objects that even James Webb will not have. And so if they can come along in about the same time frame as James Webb, working together with James Webb, will make a big difference in our understanding of the distant galaxies, just as Hubble has worked together with the big telescopes like Keck and the VLT today to try and help us understand what's happening in the early universe.
So what you're saying, Garth, is that the future of astronomy is the symbiosis between giant ground-based and bigger space telescopes.
That's certainly a key part of it. It's something that we have seen very often. At times you need very specialized telescopes, but at other times it's different capabilities working together that really help us make advances. Having huge ground-based telescopes of the next generation, the TMT, the 30-meter telescope, the EELT, the European 40-meter telescope, these will be remarkably powerful, especially as we use them in conjunction with James Webb.
This is a very good question. What new things have we learned about the formation of the universe by analyzing the XDF?
The formation of the universe. XDF is really about galaxies. XDF is really about understanding how galaxies themselves formed and built up, the seeds of today's galaxies. The one major change in the universe occurred about between a few 100 million years and about 900 million years after the Big Bang, when, as Pascal mentioned, all the hydrogen in the universe was ionized. At that point, the universe changed from neutral hydrogen everywhere to ionized hydrogen. Galaxies are the most likely culprit for that, highly likely. So when we're studying these early galaxies, we're also studying the effect of these galaxies on the universe as a whole. But for cosmology, which is more an understanding of the nature of the universe and how it's changing, XDF will not add a great deal of knowledge to that explicitly. Those questions are much more to do with the great questions now of the nature of dark energy and the changes in the universe in the future. Pascal, anything you want to add to that?
Yeah, I think the difficulty in understanding the build-up of the universe from looking at galaxies alone, is that it's very, very difficult to predict from, for instance, just starting from dark matter and the atoms that are coming with the dark matter, how stars are forming, how galaxies are forming, and so that's a very, very messy process. And so we are learning a lot about the build-up and the formation of galaxies with this new image, but not, as Garth was saying, about the universe and the expansion and so on. Yeah.
Great. Well, we're coming up on the new hour. I think we're going to cut things off here. I want to thank each of our guests. This has been, I hope for our audience, this has been very mind-expanding. A lot of great questions about the fundamental nature of the universe, the evolving universe. And we live at such a special time, we can actually talk about these things. These things were philosophical for thousands of years, and we can look at real data. So, but the adventure continues. So I invite everybody to come and visit hubblesite.org, where new discoveries are coming out from Hubble all the time, and no doubt we'll even have deeper pictures in the coming months, as Garth said. With that, I want to thank everybody, and we'll do this again sometime. Okay, thank you.
Good. Thank you, Ray, and thank you to all the audience and their great questions.